So we are starting with machine learning today, and so I think Saptarshi had give you an idea about what is supervised learning and what is unsupervised learning. So machine learning are two types. So supervised learning, in case of supervised learning, there is a y variable there, and you try to predict the y variable using multiple x variables that you have. However, in the case of unsupervised learning, you do not have a y variable, and your outcome of the model is that y variable. Basically, your outcome of the model is a, a grouping of the variable of the observations into multiple groups. So there are various techniques to do both supervised and unsupervised learning. One of the very basic techniques for supervised learning is k nearest neighbor algorithm. So what is this algorithm talking about? So here also there will be some x variables involved and there will be a y variable involved. And we will try to predict the y using the x variables using a simplistic methodology. So the idea of this particular observation of this particular algorithm depends on this particular logic that a person is like his friends. So you become whoever is your friend is, you basically become like them over time, which is true. We can see that so there is something called homophily where people like to be with people who are similar, or people who have the similar kind of characteristics show the similar kind of pattern. So this particular algorithm also believes on that. So what it says is that if I have a data set and if a new observation comes in and I have to predict that what will be the y of this new observation where the x values are given. So what I will do is that based on the x values, I will try to find out what are the various observations which are close to this particular observation. And I will find out, let's say, observation 5, observation 9, and observation number 124. These are the three closest observation in terms of the x variables. So then the central tendency of these three observations will be basically my prediction of the y. So if y is categorical, the central tendency will be mode. If y is continuous, the central tendency will be mean or median. So in most cases, we take either a mean, and in categorical cases, we take mode. So that is the overall basic idea of k. So if I move ahead, so I talked about what is supervised and unsupervised. In the supervised, we have level data with class as the level. In unlevel data is used for unsupervised data. Now the concept of distance, when I say that who are the nearest neighbor, the concept of distance is very peculiar, and it depends on how you measure the distance. For example, let's think about this chessboard and think about the think about this king. So for the king who is standing at the middle of the chessboard, the green tables, basically green boxes, are one move away. So the distance from the green boxes to the to the king will be 1. Similarly, the orange boxes are 2 moves away, and the red boxes are 3 moves away. That's how the king perceives its distance. However, the rook has different kind of movement. Rook moves only at the only side by side and perpendicularly. So for rook, all these green ones are basically one unit distance. That those are one move away, and all the orange ones are 2 moves away. So the rook can reach to any of the orange box with 2 moves. Now, if I think about the last one, which is a K rook that combines the restrictions of king and rook, now it can move only one square at a time and only horizontally or vertically. So this is the thing that I'm saying, that either it can move horizontally and vertically like a rook, and it can also move only one move at a time. So which is like the king. So we call it K rook, which is a fictional one. For it, the green ones will be like the only the one which is adjacent and horizontal and vertical. This one will be one move away, this four. And then the orange ones will be two move away, and the red ones will be three move away, and so on. So that's how the distance is perceived. So all I mean to say that the distance perception will be depending on what kind of restrictions you have. Similarly, for this bishop will not be, if it's a white bishop, it will not be able to go to the black boxes ever. So bishop, for bishop, there will be many places inside the chess box which is not accessible at all. So similar kind of problems also comes up when we perceive distance. So when we perceive distance, what I'm trying to say here by showing these measurements are that it can be a factor that certain factors gets more importance and certain factors has absolutely no importance when we are measuring a distance in a particular context. Let's say I'm trying to predict the non-veg eating pattern, how much non-veg somebody eats in his daily life. So I took many people's data. The one variable that has come up in this thing is that gender. Let's say gender is one variable, native place is one variable. So I got one classroom of students. I took all their data, and I also took their y variable, that how much they eat this thing, non-veg. Now a new student comes up and his data is also available, but I do not know how much non-veg he eats. I have to predict that. So I have to find out similar students. The similarity will be measured by what? When non-veg eating is the variable of concern. Probably the native place is a very important variable, or the geographical location is a very important variable, or probably gender also. So men eat more, generally consume more than female. So probably that will also impact. Even if you non-vegetarian or vegetarian, the generic consumption pattern will impact based on the gender. So these are some of the variables that I take. However, let's say whether the person is bald or not, or whether the person has a mustache or not, or whether the person wears a spectacle or not, these are also variables. These are also data set that I have about that person, but this might not be that important. This might not have any effect on the overall prediction of whether somebody eats non-veg a lot or not. However, if the y variable was by any chance, let's say whether the person had headache or not, in that particular concern, probably whether the person is bald or not, or whether the person has a spectacles or not, have more effect than his native place or his gender, his or her gender. So depending on the y variable, the x variables which contributes towards this distance will change. And that is very important thing to choose, because at this moment in KNN, we are using all of them to be of same importance. We are not measuring the importance of the variables. We are just thinking that all the variables, those are important, I will take them, and then I will calculate the distance. So this is an important choice, first of all, that what variables will be included in the model, what variable will we consider when I'm measuring distance. The distance can be also of different types. This is another choice that becomes an important variable. So just now I told that uh, uh, these two moves away or three moves away, and etc. So there are different ways to measure distance, and that is sometimes in sync with this chest weighing that I was talking about. So some of the basic distance, mostly used distance in metrics in the calculations are Mahalanobis, Hamming, Minkowski, and Euclidean. So let's discuss about each of these distances. What is there? What is in it? What are the pros and cons of these distance measures? And then we'll go ahead. So Manhattan distance and Euclidean distance are very easy to measure. These are some of the so Manhattan distance is basically the distance of, you can say, the rook, how the rook moves. So the distance between point X and point Y, so that will be not point X and point Y, basically it should be point 1 and point 2, and the X-axis is in the horizontal side and the Y-axis in the vertical side. So from this point to this point, the distance will be the X-axis. What is the distance, which is x1 minus x2. Let's say this is x1, this point is x1, and this point is x2. So this distance is x1 minus x2, and I take a mod of that because I do not know whether x2 is higher than x1 or x1 is higher than x2, plus y1 and y2. So basically it is the horizontal and vertical distance. I add that up. It's like how the rook moves. That's Manhattan distance. However, Euclidean distance takes the I would say hypotenuse. It takes x1 minus x2 square plus y1 minus y2 square and a square root on whole of it. So this equation is a little bit of so be careful. It is basically x1 minus x2 square plus y1 minus y2 square, and the square root will be in the whole of this thing. It's not x1 minus x2 square and then a square root plus y1 minus y2 square and then a square root. This is wrongly written. So that is Euclidean distance, and we heavily use Euclidean distance for our measurements, but sometimes we have to check that whether by any chance Manhattan distance is giving better results or not. Because there is, I will come to talk about the black boxness of any kind of machine learning model. But these are the two distance measures that are available.
Sir, I have a question. I mean,
Yes,
for
I will stop here.
Euclidean distance, so why it can't be x minus y or y minus x mod? I mean, could be that simple, but then the formula which
So
we've
this is
noted
basically
is
written wrong. Means let me just put it in this way. The picture and the whatever is written is basically wrong.
okay.
Just 1 minute. Yeah, this should not be. This should be like this. It's not x and y. The points are not x and y. This is y-axis. This is x-axis, and that then this formula is correct. If the points are x and y, it will be x minus y, x as a vector and y minus y as a vector, square of that and root. So not square of that. Basically, x as a vector minus y as a vector. That will be the formula. If by chance I take this point as x and this point as y, then I have to assume that this point is basically a vector point and y is also a vector point. And then x vector minus y vector will be the Euclidean distance. So it has not been written correctly. This particular thing has not been written correctly. It should be x1, y1 and x2, y2. Or otherwise, they should have written like this. Let's say there are 2 points, A and B. Let's say these 2 points are there. And so origin 0. So origin to A is A vector. Origin to B is B vector. So this is basically A vector minus B vector. This is Euclidean distance. If they had written like that, then it would have been correct. Otherwise, they should write it like this. Okay, fair enough.
Yes, sir. Okay, so one thing which I was thinking is this x1 and y1, x2 and y2. So are we seeing these two values from a certain point, like you've shown there O and then A, B, or I mean these are just the
No, let's say I have two observations. Let's say I have one observation is which looks like this. Just 1 minute. Let me just add one slide here so that I can discuss. Let's say I have two observations. One observation is uh, the income, and another observation is experience, let's say, or education and experience, and I'm predicting income. Let's say not income. Let's say education and experience. So let's say these are the two videos. And after normalization, the first person, serial number 1, has got 0.4 here. What is happening? One minute. There's some problem coming. 0.4 here and point, let's say, uh, 0.6, and this is 0.3 and 0.2. Let's assume. So in such a case, if this is the case, then the distance between these two will be 0.4 minus 0.6 square, 0.3 minus 0.2 square, something like that. So I am measuring the distance based on the observations that I'm getting. I don't know what is happening to my pen.
and also shouldn't it be the under root of
So I have to take a square root of it. I have to take a square root of it. So distance square is that value that I'm saying. Now I can, if I have a new observation like this, let's say uh, in practicality, let's say I have 1, 2, 3, 4, 5 observations, and education and experience I told, and this is 0.3, 0.2, 0.5, 0.4, 0.7, and this is, let's say, 0.5, 0.6, 0.9, 0.2, and 0.5. And I have their corresponding income also. The income values are, let's say, income value has also been normalized, and after normalization it's a 0.4, 0.8, 0.9, 0.3, 0.6, let's say. Now a new person comes in, and this new person's is 0.5 and 0.8. Now I have to find out how this person's income is. What is this income? This I have to find out. So what I will do, I will find out the distance of this person from each of these things. So let's say if I use Euclidean distance, then it will be basically, I don't know whether there is a dist function or not. So dist is for distribution. Just 1 minute. Euclidean distance is not there anyway. So it is square root of this minus this value, square of that plus this value minus this value, square of that. Okay, so this is my square root distance. And before I drag, I just put a F4 on B8 and C8. So now I drag it, and these are the distances for each of these observations. So now what I will take here, I can take the k nearest neighbor. So who are the k nearest neighbor? So if I just find out the rank, or rank or what? Rank is the thing that we use. Let's see, just 1 minute. Rank of this number in this particular thing in an order of rank means what? It should be descending, right? 0. And then if I, before I, this thing, I will fix it. F4, F4. That means what is the rank of E2 in the order E2 to E6 in a descending order? So if I do that, I will find that this is my rank 1, this is my rank 2. These two are both have same rank. So if I just change a little bit, let's say this is 0.4 and this is, let's say, 0.2. Okay, now I have 3 absolutely different ranks, okay, for all these observations. So now you see, this is rank 1. This has the highest distance. This is the distance matrix, right? This has the highest distance. This is the second highest distance. This is the third highest distance. So the nearest 3 neighbors, if I consider 3 neighbors, the nearest 3 neighbors are basically these 2, 3, 4, 5. So 0.477, 0.1, and 0.36. These are my nearest 3 neighbors. And their corresponding income is like that. If I take an average, I can take an average of 0.6, 0.9, 0.8, and that will be my prediction. I can do that. Or I can take a weighted average. Instead of taking an average only, I can take a weighted average. I can do a, let's say, something like this, that 0.6 into 1 by this distance plus 0.9 into 1 by this distance. Why 1 by this distance? Because weight should be inversely proportional to the distance, right? Into 0.8 into 1 by this distance divided by 1 by this distance plus 1 by this distance plus 1 by this distance. So this makes it a weighted average. I can take this, or so just write it out. So if it is 0.83683, I'm just writing it out. 0.83683 was my first, And another prediction was what? Another prediction was this comma this comma this, which is 0.76667. Now using one of the method, I can change it. This one I have used Euclidean. I can change some other method and I can get some other prediction. So there can be 4 or 5 different kind of predictions. We'll check which one is giving the highest root mean square error. So this is the basic algorithm of KNN.
Sir, question is, if I have my independent variables and my dependent variables, is it advisable to use KNN or do we go for a predictive model like regression?
I didn't. Can you be a little bit louder, please?
So basically, we are going with unsupervised learning here, but since we already have a dependent variable, should we not go for a supervised learning?
No, we are not going for unsupervised learning. Here we are going for supervised learning only.
Okay,
What do you say I'm going for unsupervised learning?
Because we are calculating the distance between basically from the new point and to the old point, but we are not using the income and inputting the y values to train the model, right? We are using,
yes.
So this is unsupervised, right?
No, this is not unsupervised. This is supervised learning, but we call it lazy learning. The lazy learning method says that the model will not start learning unless the test data is there. It will only do the learning only when the test data is there. Till the test data is there, it will not start learning anything. So it's a supervised learning only, but it's called lazy learning method. So KNN is that kind of a method, which does not learn on its own from the data set. Only when the test data is available or the validation data is available, that means outsample data is available, only then it will start learning.
Yes, but test data in the sense that this new is the test data.
New is the test data, yes.
Okay, so once you get the test data, you calculate the distance and then you use the income to income value and populate that income value. But way more of okay, so I was thinking this not slow. But again, my question stands. So, is it better to use the regression here? Say, because we have the income and we have the data, right? Five data points. So we can have a equation, regression equation, and then predict. So, will that hold better? Will this KNN?
See, the better or worse this question will come out ultimately based on the RMS score. Better and worse. So there are various things that is involved to when you try to answer the better and worse. If you try to answer that what affects your income, education or experience, this method will not answer this question. Not only this method, no machine learning method will be answering you this question that what impacts income, education or experience. You have to rely on regression. So all the predictive models which tries to find out the relationship between x variable and y variable, regression will always be better. However, when you are trying to predict a future outcome or a outsample outcome, that means this is this value, which is outsample data, and its outcome you are trying to predict. In this prediction problem, whichever is giving you better result is better. There is no thumb rule that regression will be better or KNN will be better or some other algorithm will be better. But KNN has some advantages and disadvantages. We'll come to that as I move ahead.
And sir, in case there are more than two variables, so basically you have a special distance. If you have three variables, then if you go higher.
Yes, if there are three variables, then my Euclidean distance will have three components in it.
Yes, and it will increase exponentially
as the number of variables increases, the distance measurement does not increase exponentially. It increases in the linear way. However, as the number of observation increases, the calculation increases exponentially. Let's say instead of one observation, so right now I am calculating 5 distances. But if I have 5 observations here, I would have to calculate 5 into 5 distances. Right? So 25 distances. So with every increase in the testing data, the calculation increases non-linearly. So that is a challenge. That is a fallback of KNN. We'll discuss about that. So okay, let's move ahead. Some more distance metrics. So in general, distance has to be greater than or equal to 0. Distance has to be symmetric. That means distance of xy has to be similar to distance of yx. Detours cannot shorten distance. So if I want to take x to y versus if I want to take x to z and z to y, so distance of x to z has to be smaller than x to y and y to z. So the detour will never cannot shorten the distance. This is something that when you create a distance matrix, this is something that you have to keep in mind. So Hamming distance is basically this again. It has multiple I would say uh, observation, multiple what we call the axes, and the distance from the because it has three axes or multiple axes. It actually measures distance based on the a cube's position. Basically, instead of x and y, it is taking x and y and z. So, like 0, 0, 0 and 1, 0, 0, 0, 0, 1 are and probably this 0, 1, 1. 0, 0, 1, 1. This is these three. The red lines are basically one distance away, and 0, 1, 1 should have been basically black. It is also two distance away. 1, 0, 1 is also two distance away, and so on. So Hamming is also using these perpendicular lines in the context of a cube to measure the distance. So just 1 minute. Just hold for a minute. So the basic concept of Hamming distance is coming from a vectorization. Basically. So let's say it is used in categorical data. Let's say I have two vectors and I have this 1, 1, 0, 0, 0, 1, 1, 0. Let's say this is observation number 1. These are all categorical data. Okay. Observation number 2, it is, let's say 1, 0, 0, 0, 1, 1, 1, 0. Hamming distance will only say that in which positions the values are different. Now, you see, if I had used Euclidean distance here, it would have been 1 squared plus 1 squared and root of that. That would have been the Euclidean distance. Here there is 1 square, here there is 1 square, and that like that. Had it been this distance, which is Manhattan distance and this distance is more or less same in the context of 1 zeros. So Manhattan distance would have been basically 1 minus 0 mod of that, plus here also 0 minus 1 mod of that. So 1 plus 1 is equal to 2. Same thing comes for Hamming distance. The Hamming distance is just measures, but Manhattan distance is applicable even if it is not categorical data. Hamming distance is applicable only when it is categorical data. It checks that which positions, how many positions they are not similar. So this position it is not similar. This position it is not similar. So I put 2. That's how. Now, let's say if by chance if it was not categorical data, it was a continuous data, then this value could have been zero point 0.1 and this value could have been 0.1 also. So Hamming distance would have been measured, Manhattan distance would have been measured 0.1 minus 0 and 0 minus 0.1. That means 0.1 plus 0.1, which is 0.2. However, Hamming distance would have still measured 2, which is 0 and 0.1. There is one place where they are different. This is also another place where they are different. So this distance would have always been 2. That is the basic difference between Manhattan and Hamming. Manhattan will be applicable in categorical data and it will treat categorical data and continuous data differently. Hamming distance will not do that. Hamming distance will treat them in a similar way. And then the last one is Minkowski's distance. So Minkowski's distance is basically it is not it is a little bit about related to this a generalized version you can say of both the Hamming distance and sorry not Hamming distance it is the generalized version of both Manhattan distance and Euclidean distance. If you see that if I take m is equal to 0 here, sorry, m is equal to 1 here in this particular measurement. So xi minus yi, or they are taking it xi minus yi, I should have taken if there are two values, let's say x1 minus x2, y1 minus y2, z1 minus z2, and so on. I do not know how many other distances are there. What I'm taking is I'm taking this to the power m, this to the power m, this to the power m, and so on, all to the power 1 by m. That is my Minkowski distance. Now, when m is equal to 1, it becomes basically Manhattan. It's a generalized form. M is equal to 2, it becomes Euclidean. So I can generalize. Why will I take square? Why can't I take cube or to the power 4? So that is basically answered by this particular question by using dxy, which is x minus y double this thing m. Then there is Moholy-Nagy distance, Chebyshev distance. There's other distance formulas are also there. We'll not go into this detail, but these values are also there, which sometimes are used in measuring. So for example, nowadays people are using Moholy-Nagy distance a lot. It helps in PCA kind of algorithms. We'll discuss PCA at the last day of this course, and we'll in that particular class I will discuss about Moholy-Nagy distance in a further better detail. Now, all I'm trying to say that the distance measurement is you can use different kind of distance measurement. Now, how to use it? Now, when I'm doing the mean, I can also use different kinds of mean. I can use arithmetic mean, I can use geometric mean, I can use centroid method and Maynard method, etc. So arithmetic mean is something like this, you know. It's if I have 3 observations like 2 and 4, it's 2 plus 4 plus 3 and so on. So you know what is arithmetic mean. I'm not spending time on that. Geometric mean is a term between 2 terms of a geometric sequence in the geometric mean of the 2 terms. So basically, if I have multiple values and I want to find out the geometric mean, I have to multiply them and divide and take a power of 1 by the number of observations. So that's the geometric mean. We can use that. So in the nearest neighbor search, a set P of n points is there, and the goal is the data structure which is given a query point Q. If I have a point Q, find the nearest P of the Q in the overall P set. Means capital P is the overall set, and the small p is one observation in the capital P. I have to find out the nearest neighbor of Q. And the nearest neighbor of Q will be one value. If I want to find out multiple nearest neighbors, then it will be P1, P2, and P3 or something like that. So in KNN, so reduce complexity by having a threshold of majority. So we should restrict the associations to k minus 1 in it. So for example, k is equal to 5. Let's say this is my red cross is my observation. The 5 nearest observations are the ones which are somehow and in this particular picture you might say that why the red ones are coming. It's a two axis representation of the data, but the data can have multiple axes, and based on some other axis probably this particular value is coming closer. So these are my 5 values. I found out these are my 5. Okay, sorry. The X's are some category and the red ones are circular ones are some category, and I have to find out whether this one is circular or X. So I find out the nearest 5, and based on the voting system, I found that the highest possibility is that I will be a square. I will be a cross. So that makes a prediction of cross. So decide if majority of instances over a given value of k, here k is equal to 5. So this becomes a cross. Similarly, let's say this kind of an example. Let's say acid durability and strength, and the classification is bad or good for a particular variable. So, and their corresponding x variables are given, and a new observation comes in, which is 3,7. I try to find out whether it is good or bad. So I can find out what is the xy in this kind of a plot. What is the distance between this particular point, which is 3,7, with all the other points, this point, this point, this point, and this point. I find out that, let's say I use Euclidean measurement, and I get 4, 5, 3, and 3.6. Now I can choose what will be my k. If my k is 1, then the corresponding, I will be taking whatever is the P3 as well. If the distance is k is 2, then I will take an average of P3 and P4, and so on. So let's say 3 nearest neighbor if I take, then P1, P3, and P4 I took. P1 is good, P1 is bad, P3 is good, P4 is good. So the mode of them is good. So I will predict myself to be good as well. So I'm writing it good. Similarly, I can vary the KNN. I can change the number of Ks. K is equal to 3 will give some result. K is equal to 7 will give some other result if I check here. So for example, when I'm taking in this particular thing, the two options are blue and green, and the red ball is an unknown ball. I want to predict what is this ball. If k is equal to 3, the prediction is coming to be green. And if k is equal to 7, it is coming to be blue. So sometimes this instability comes up, and we have to try out multiple k values to check that which one is giving the best result. Now, the calculation, there are certain advantages and disadvantages of this thing. So this one primary advantage of this model is that it is easy to understand, easy to interpret, easy to use. But you will know that as somebody was asking, that why it is not starting learning unless there is a testing data. That is a problem. It will not create the model beforehand. It will start predictions or start calculating with the model only when the predicting variable, the test data is there. Now that is a disadvantage. What kind of disadvantage? Sometimes we need instantaneous predictions in many cases. Let's say a particular person has come up in your website. You have less than a millisecond, probably less than a millisecond time to predict in which group So less than a millisecond time to predict in which segment this particular person falls. Let's say you have in your past data, you have many customers data and corresponding segments of those customers. Okay, so segment one or segment two or something like that, you have that data. Now, whenever a new customer comes in, you have to basically predict that in which group, in which segment this particular customer will fall, and based on that, you will probably change your website's design or website launch. That the website will launch differently. Now, this prediction has to be very instantaneous. You cannot give a lot of time to predict that which customer group this particular customer will fall. Now, if it is a lazy learning method, if it starts learning only when the data is arriving in front of you, and then it takes probably 1 minute to predict, then that creates a problem. Further, there is a huge dimensionality issue. As I was just now giving an example, that I have to find out. So to calculate the closest, even if I take k is equal to 1, even if I take k is equal to 1 in this data set, in this calculation, let's say I want to calculate and I will be predicting based on the nearest neighbor. So there is no point of taking mean, median, or mode or something. Whatever is the nearest value, I will take corresponding to that. Even for that, I have to calculate the distance of this value with all the values. So this calculation is irrespective of number of k's that you take, that how many distance you will calculate. And the distance that you calculate, the number of distances that you calculate is non-linearly increases as the data size increases. If there are 5 data points here and 1 data point here, it is 5 into 1 distance. Now increase each side 10 points. Let's say instead of 5, it becomes 15, and instead of 1, it becomes 11. So that becomes 15 into 11, 165. And 165 minus 5, that means 160 points. So you increase 20 data points in general, and the calculation has come up to be 165. If you increase 200 data points, let's say 100 there and 100 there, the total calculation will increase by 10,000 amounts, so 10,000 numbers. So it's a nonlinear increase in the number of calculations that you have to do, which is a very big challenge when you are dealing with a big data. However, the prediction accuracy is very good. It has been seen that if you can give time to KNN, KNN gives you prediction accuracy almost as good as very sophisticated techniques like decision tree or neural network, much better than linear regression. So this is also another plus point of KNN, but it will take time in calculating this. So that is it about KNN. It's a very simple method. We will try to implement it using Python, and then we will move ahead to some other algorithm in the next class. Any question as of now? Okay, so let me share one file in this chat box. Can I share a file in this chat box? So please download this file, KNN with Python. I have shared in the chat box, and we will use this file. So we'll take a break for 5 minutes, and after that we will implement this KNN file. We'll run this file and see the codes. It's an easy code. It's not much to discuss, but still we'll do that, and that's why we close. So let's wait for 5 minutes, and I will come back at let's say 11, 11.5. Let's come back at 11.5. So I will be showing you two use cases. One is on this prediction of this thing in the context of a categorical data, and another is a continuous data. So sklearn is a library that we use heavily in the context of machine learning. So I have already installed it. So from sklearn.neighbors, this from this particular sub package, basically, I'm importing k neighbors classifier. This is the function that I'm importing. Similarly, from model I want to see the data set, let's say. So this data set is an array, and you see there is a target also. The target is 01 target. It's a category 012. So the target is a categorical target, and the data frame. So this target names are basically Setosa, Versicolor, and Virginica. So these are the three different types of IDs. IDs is basically one kind of a flower, and these are the three different kinds of flowers. So 0 is stands for Setosa here, 1 stands for Versicolor, and 2 stands for Virginica. And there's various parameters that are stored here in this particular data set. So this parameter names will be written later point of time. I will just check whether the parameter names are written here. No, the parameter names are, yeah. So this sepal length, these are the features. So feature names are written here. The sepal length in centimeter, sepal width in centimeter, petal length in centimeter, and petal width in centimeter. So these based on the shape of the sepal and petal, we are trying to find out that what kind of this what kind of flower this particular guy is. So I am putting the data part array, basically this part. This is the data array. I'm putting the data array which has see each of these rows has 4 entries. Okay, in the array, each of these values has 4 entries. So I'm putting the data array in this X, and then target array in Y, and separating it out from the data set. And then I'm using this train test split. This is from sklearn. I have already loaded it here. Train test split, I have already loaded it. So I'm loading it from sklearn. I'm putting this capital X and Y here, and I'm asking it to break. This train test split will break this capital X and Y into training data and testing data. And how this will be done? I am saying that the test size is 0.2 and the random state is 42. Random state is 42 is basically you are making this result reproducible. So whatever training and testing data that you are getting, and whatever training and testing data that I will get using the same random state will be, those data sets will be same. If I use the same random state and same input variable, even after the random split, the outcome will be same. So this is how the model becomes reproducible. So I am just running this. So it has run. So let's just see what is X underscore train. So if I just want to see X underscore train, that part only, it will be an array of the training data and randomly chosen training data. So not all of them are there. So some randomly chosen training data sets are available here. Similarly, Y is there and so on. Now, I am saying that set KNN with number of neighbors as 7. This is not a this is a KNN object that I am creating. And this object, then I am saying that KNN.fit is X train comma white. So create the fit of this KNN, the fit information using the training data only. And then this particular data will do nothing at this moment. If I had created a linear regression, it would have fitted something. But as of now, this guy is doing nothing. Then I'm saying that calculate the KNN score using the test data and Y test data. Now it will start the calculation actually. So using that, if I run this, I'm getting the KNN score for testing data as 0.96666, which is the accuracy level of each of these observations. Now I can try to find out the values also. Just 1 minute. I am getting the KNN score. How to get the KNN values? What is the KNN prediction values? Just 1 minute. It will give me KNN.predict X test. Yeah, so this is the predicted values that I'm getting. That is being compared with this Y test, and that's how I'm getting the results. Just hold for 1 minute. I'm getting a call. I have to take this one. Just hold for a minute. So coming back, so this is how we am predicting it. This is the first time this KNN is using this predict function. And in this particular score, they are using predict function. At the same time, they are comparing this predicting with the Y test and giving me the accuracy of like 0.96. Now, this is a test. These are dummy data. In real life, you will not get this kind of an accuracy. But any accuracy higher than 85% or 80% is good actually. You can say that is pretty giving pretty good result. Now I have chosen n neighbors as 7. Question comes up is that why did you choose 7? Why can't I choose something else? So that is what I'm going to test now. So I am creating a neighbors which is a range from 1 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All the 9 values will be taken. And the length of neighbors, you see, I'm creating 2 things. So let's put it separately. Let's do one thing. Let's put it separately. I will add this thing here. You see what I'm running. After running this, oh, okay, I have to import NP. That's fine. Import numpy as NP. Yeah. Now, if I see what is neighbors, neighbors are, this is neighbors that got created, an array from 1 to 9. So it starts from 1, ends at basically 9 minus 1, 8. So 1, 2, 3, 4, 5, 6, 7, 8, these 8 values are there. So what is the length of my neighbors? The length of neighbors is 8. If I run this, it will be 28. Now what I'm doing is this length of neighbors I'm putting here. That means I'm basically putting 8 here and creating an empty cell, np.empty8 is basically a empty set. Okay. And these values are all very close to 0. You see why it is so high value. I'm not getting it. This two should be also very close to 0. Just 1 minute. Yeah. And this is what I am creating in train accuracy and test accuracy also. Basically, I'm creating blank cells. I will later change them. So this is my train accuracy. And these are all very close to 0, you see. And then these are also test accuracy. some random, close to zero random numbers are created, and I will use this train accuracy and test accuracy. I will change these values. So what I'm doing next, I am running a loop for I and k in enumerate neighbors. So in the neighbors, I will populate those neighbors, and I will say that k in this, kn is n neighbors is equal to k, and I am fitting this value. Kn dot fit is x and y train. Then what is the train accuracy score? The train accuracy score is when I am doing kn dot score using the train data, and test accuracy score, ith score is when I am doing kn with the test data. And basically I am populating this training data and testing data. There are 8 empty cells. Each cells are getting populated, one for training data, another for testing data. In each of these things, the k values are changing from 1 to 8. So if I run this, and now if I try to check what is train accuracy, this is the training data's accuracy level with taking k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4, and so on. And if I take, see, k is equal to 1, why it is coming 1? Because when it is taking nearest neighbor is 1, it is basically taking itself on. In the training data is being measured based on training data only, no? So I will be in the training data, I will be closest to myself. And when I take k is equal to 1, the prediction is exactly coming to whatever I am. So that's why the accuracy will be 1. So when you take k is equal to 1 in training data, it will be always 1. But this has nothing much to do. Basically, train accuracy has not much to give you. But test accuracy is something that will lead to what choice of n will you take. So in this particular case, it's a sample data set. I'm getting very good accuracy if I take k is equal to anything other than 7. So all else are giving accuracy as 1. So I can take anything. Ideally, these will be different values. In an ideal case, this will be different values. And whichever is giving you the highest accuracy, will choose that k as your model parameter. So that's how I'm optimizing the model. I can plot them also. I think matplot is not there or what. I think I have to import matplot. Just 1 minute, I forgot how to import mat. This is a very common code. Yeah, so I'm PLT, I'm matplot library, spyplot as PLT, I'm importing it, and then I want to run this plot. What I'm plotting 2 lines. One is testing data accuracy and the training data accuracy. And I'm putting the legend also. The X levels are n neighbors, the Y levels, this is the n neighbors, the X levels. The Y level is accuracy, and plot show. I am asking to show the plot. So that's how a plot gets created. So whatever these 2 things basically connect, I have chosen 7 because this is why these two graphs are connecting. I want to avoid overfitting, and I want to have a better accuracy also. So I have to check that where these particular 2 plots are meeting each other. That is where the overfitting and the bias and variance gets balanced. Now this is we are using when I am using a categorical data. I can also show you how to use it in a continuous data. So one such data set I'm going to use, which is called Avalon. So let me just read this data set. So it is a publicly available data, and the data set looks like this. So here the last column is the number of rings. So Avalon is the one kind of a I would say animal basically, which has the rings, and the rings are basically the measurement of how old this abalone is, and it has different other variables which also can be. Now measuring these other variables like the measuring the rings is difficult. It sometimes it has to be cut to exactly measure how many rings it has. The more the rings, the better it is. However, the rings can be predicted using the sex, the length, the diameter, height, hole weight, suck weight. These variables are easy to measure. So, can I predict the number of rings in a particular abalone using these variables is the problem. So, I am putting this variable names. And now if I want to see the abalone head, it looks like this. So, sex, length, diameter. So, these are my x variables and this is my y variable. So for our purpose, I am dropping x because x is a categorical variable. You have to create a dummy out of it. But for our simplicity purpose, as of now, I am dropping it. So I'm dropping it, and now if I want to check the abalone, so the sex has been dropped and other variables are there. Now, if I want to plot the rings histogram, the histogram of rings looks like this. It is more or less a little bit skew in the right side, and it has a mean of, let's say, close to 10. Median will also be close to 10. So that's how it looks like. I could have also run a very good linear regression using this model because it more or less looks like a normal distribution. And the rings variable, if I try to see the correlation with the other variables, I can see that they are fairly correlated, 0.5, 0.57, 0.55. The normal correlation is pretty high. So a linear regression could have actually worked pretty well. So if I have to compare KNN with any other variable, I have to basically compare with the linear regression model as a benchmark. Now what I'm going to do, I will be showing you what exactly this KNN does in hand. And then I will be using a library as I was using before, KNN classifier. So it uses a algorithm which is like a Euclidean distance. Let's say I have two arrays, 2, 2, and 4, 4. So this will give me 2 minus 4 squared plus 2 minus 4 squared and square root of that. This particular guy will give me 2.828. So this is my distance measurement variable. So now if I use this variable in x and y, let's say all the x I keep it in x and all the y values I keep it in y. And then I have a new data point like this. These are all x's in the new data point. What I have to do, I have to measure the distance of this new data point with all my x values. So if I just measure the distances and run what is this distances quickly in front of you. This is the distance of the individual observation, this observation with all my other x values. So these are my distances. And I have to find out who are the nearest neighbors. So what are the distance of the lowest? And I chose k is equal to 3. So the IDs where the distance is lowest is 4045, 1902, and 1644. Out of all my observations, these are the 3 IDs where the distance is lowest. So what will be my prediction then? Basically, these rings I will take what are the IDs corresponding rings. The rings are 9, 11, and 10. And I take a mean of that. That is my prediction, which is like 10. What is the prediction? So if I just write prediction, that is coming to be 10. So 10 is the prediction because it's an average of 9, 10, and 11. So now this is for one observation. I will actually do it for multiple observations using doing this. So what do I do? I again break my data set into training testing as I did before. And I create a KNN neighbors with n neighbors is equal to 3. By 3, I can change 3 later. So right now I'm starting with 3. And I'm getting a model fit using the same data set, using this KNN model. I am predicting using the training data. And with that prediction and the Y training data, actual values of the training data, I am calculating the RMS score. So the training data's RMSE is coming as 1.65. But actually, we will not bother about the training data's RMSE. We will rather focus on the testing data's RMSE. So I can basically quickly calculate the testing data's RMSE also very quickly. When k is equal to 3, the test predictions are X test and this Y test and test spreads. And the testing data's RMSE is 2.37. You see, it always fits better here in the training data than the testing data. So this is my testing data's RMSE. Now I have to probably try to improve this as much as possible. How I can improve? I will run a loop. So here I have used a grid search kind of a algorithm. Grid search is also search algorithm where the range is 1 to 50. So 1, 2, 3, 4, up to 49. I will be use all these parameters and do a grid search. So grid search is basically, it's a optimization algorithm which where a function is the first input that you give and the parameters is the second input that you give. Now k nearest neighbor, this particular function, if you remember before, k nearest neighbor, this function has only one parameter in neighbors. So that's why here I am first telling that n neighbors will be having a range of 1 to 50. If there were two parameters, I would have written parameter 2 will have a range of something else. So I would have written that. But here I have only one parameter, so I am writing only n neighbors. And this parameter list is given, the function name is written, and grid search will give you the which parameter value gives you the best result. And then you fit it with using Xtrain and Python. So once I run this, it will basically testing it for all the values from 1 to 50. And it is saying that the best parameter result is coming at n is equal to 25. So when you are taking the nearest neighbor as 25, that is the best result. Using that, if I want to print the training and testing RMSE using the same formula that we used before, training and testing RMSE, I'm getting the training RMSE as 2.07 and testing RMSE as 2.17. You see that training RMSE has increased because I have taken more data set right now. From 165 to 2.07, the training RMSE has increased. But testing RMSE, that means outsample validation of this particular model, has dropped from 2.37 to 2.17. So I am getting better outsample results right now. I can have further parameters. I can say that, okay, not only n neighbors, the weights can also be taken. So for example, remember in the Excel, I do weights to be uniform or weights to be distance, inverse to the distance. So the higher the distance, the lower the weight. So these are possible choices. And I can ask grid search to tell me that what will be the optimal choice. How? So then now how many choices I have from 1 to 49 for all these 49 different k values. I have two choices in each of them. Either to go with uniform or to go with distance as my weights. So I again do the grid search. It is saying that 25 is the optimal, that's fine. But in that case, you take weights as distance. That means 1 by distance you take basically. So if that is the case, again using that, I calculate my RMSE and I'm getting further lower RMSE, 2.1634. So this is how you can slowly optimize your model for your external data. You should not optimize your model in a prediction problem for your internal data one by one. So these are the two models that I have used. In the first one, that is continuous data. First one was categorical, second one was continuous. In categorical, you use accuracy. In continuous, you will use RMSE score. In a later point of time, you will learn other measure scores like F1 score, or let's say specificity, and recall, etc., etc. We'll learn that. We'll discuss about that. But as of now, let's take accuracy as the measurement, and in the RMS score as the measurement. So as we go ahead, we will talk about two more things. I think software will cover in the next class, which is all the different kind of fit scores and which one is applicable at what point. And ROC curve is an important curve in the context of classification, which is the first one that we need. So how ROC curve plays a role, we will also discuss about that. So I will stop here before I close today's session. This is it for today's session. If you have any question, please let me know on the coding part. You can also do the coding on your own. We planned for a session on artificial neural network from 1 p.m. to 3 p.m. today, but I have some urgent work has come up on that particular time period. We'll not have this session today. We'll have the session later in the next week probably. Tomorrow there will be another session from like the same thing, 10 to 12 and 1 to 3, where we will cover decision tree and random forest using Python. So before I close today's session, if I want to ask if you have any question.
So, sir, there is no session after this, you're saying? Today?
No, yeah. So for today, there is no session.
Okay. So tomorrow the time is same.
Tomorrow same session, yeah, same time. No
Okay.
change in tomorrow's time. So try out this cadence. This is very simple to implement and very, I would say Python works well. See here in both the data sets, the number of variables were not very high. We had up to 10 number of variables. But as the number of variables goes up, this will create problem. However, in most of the practical cases, we do not have more than 20-30 variables. If I have more than 20-30 variables, we generally do PCA and reduce the number of variables to something like 20-30. So that we will teach in this course, how to do PCA. Reduce the number of variables. But yeah, so up to this is what we have to discuss. If you have any question, please let me know. Otherwise, we'll stop here and I will. So we will again meet you tomorrow with Saptarshi and the sessions will go on.